In this video, we're going to continue discussing these work-related problems. And so this is one of the classic chain problems. It says a 30-foot chain weighs 4 pounds per foot lying on the ground. How much work is required to raise one end of the chain to a height of 30 feet so that it is fully extended? Now keep in mind that it weighs 4 pounds per foot lying on the ground. So as you raise the chain, you're going to be holding more of the chain and it's going to be requiring more force in order to lift it. So you want to think of this as you're trying to raise the entire thing from 0 feet to 30 feet. So that's where our bounds are going to be. So I've got something that I'm using to lift it, and if this is the height that it's been lifted to at a given time, then you can see that whatever your change in y is, your delta y's here, you would do this however many times it takes you to get all the way up to y. And eventually, we want this chain being held at 30 feet. So we've divided our chain up into all these little segments. So the weight of each segment of chain is going to be equal to delta F, which we know is 4 pounds per foot times whatever delta y is, however long that segment is. And we're going to let dy be the height of the top of the chain. So dw is approximately delta w, which is the delta F times d. So that gives me 4 times delta y, because that's our delta F, times y. And if I rearrange that, I get 4y delta y. And we know that delta y can be approximated by dy. So I have approximately 4y dy. So we're going to make f of y be 4y. So what that happens then is that when I integrate, w will be the integral from a to b of dw, which is going to be the 4y dy. And we're going to integrate from 0 to 30 because we're raising the chain from the ground to 30 feet. So I get 4y squared over 2 from 0 to 30, or just 2y squared from 0 to 30. And that gives me 2 times 30 squared minus 0 squared, or 2 times 900, or 1,800 foot-pounds. So that would be my answer for this problem. This is another chain problem. It says consider a 15-foot hanging chain that weighs 3 pounds per foot. Find the work done in lifting the chain vertically to the indicated position. We want to take the bottom of the chain and raise it to the 15-foot level, leaving the chain doubled and still hanging vertically. So this one's interesting because unlike the last problem where the chain started by sitting on the ground and then you wanted to lift it up, in this case the chain is actually hanging, and we're going to pick up one end of it here and start raising it until we match it with the top, basically. So we know that our delta F, we know that the chain is 3 pounds per foot. So delta F is going to be 3 pounds per foot times delta y. And we know that F of y is going to be the weight per foot times the distance, the force times the distance. So with this one, you have to kind of think about what's going on here and how much you're actually holding. So when I'm looking at raising this thing a distance of y, that chain gets folded up and I have a Y here as well. So whatever the height of the chain is now, or the distance that it's being moved, is 15, which is the 15-foot length of the chain, minus 2y, because we're looking for the position here of the top of the piece that I'm holding. So in order to split this thing in half, our y is going to go all the way from the ground, which would be 0 feet, to the amount of chain that has been moved, which is half of the chain, or 7.5 feet. So I've got my 3 pounds per foot. I've got the distance that the chain has to move, which is 15 minus 2y. So that's how far it's going to move at a given time y. So my work then will be the integral from 0 to 15 over 2, or 7.5, whichever one you like. The force times the distance that the thing has to move at y, dy. So always the weight times the distance. So this is going to be the integral from 0 to 15 over 2. I'm going to go ahead and multiply this in, and we'll get 45 minus 6y. So that gives me 45y minus 3y squared when I integrate from 0 to 15 halves. So that gives me 45 times 15 halves minus 3 times 15 halves squared, all minus 0 minus 0. So I get 675 over 2 minus 3 times 225 over 4 minus 0. And if I were to find a common denominator and subtract those two numbers, I would get 675 over 4 foot-pounds. So this is a chain problem, and it's just one of the two variations. There's actually several more. You just kind of have to visualize what's going on in the actual problem and how it's being described. You also might want to draw a picture. This picture helps us visualize this quite a bit, because you can see that where the 2y is being subtracted off and why that would be the case. So I would recommend read it very carefully, draw yourself a picture, and see how you're going to set up your distance that the chain is traveling, and see how you're going to set up the weight that's being carried as well.